Okay, so we're going to be talking in this next section about recursion randomization and look at some examples of those. This is our final section on algorithms and computational thinking, that 25% right there of the praxis. And then we'll have a short look at data in the third slide deck after that. So take it away, Deborah.
All right. So when we talk about recursion on slide 4, we are actually talking about, sorry, before I go to explain all that, recursion, this is what ETS wants you to understand: simple recursive algorithms, that is n factorial, sum of first n integers. You again learn how to trace simple recursion algorithms. Also understand how to provide missing steps in incomplete simple recursive algorithm, identify parts of a recursive algorithm, that's base case or stopping condition, which we'll talk about, and then the recursive call, and then identify errors in simple recursion algorithm, and also identify iterative algorithm that is equivalent to a recursive algorithm. So that is what you're supposed to understand from what we cover in this section. So we will talk about recursion being a technique to divide the problem into sub-problems of the same type. So simply put, a recursion is a function that calls itself. Very important to know that, a function. And sorry, we use the word function, and we should say a procedure, but procedure, method, function is the same thing. So it's a procedure that calls itself. So recursion is usually used whenever a problem can be solved by dividing it into smaller problems. Recursive procedure is much like the Russian doll. Each time you open a door, a smaller one appears. Should be moving it that way, but that's fine.
Oh, okay.
Yeah, that's okay.
Yeah.
I was gonna move it slowly, but that's okay. Yeah, every time you call, another smaller one appear inside, and then you repeat the process until you reach the smallest, which does not contain one inside it, and that is your stop case. Sorry, we were trying to automate manually. All right, next slide. All right, so this is just a quick example of procedure using the dolls. So what would you do? You would have a doll, a procedure doll that calls itself. So it's calling itself inside. So anytime we see a name followed by open quotation, we know that that is a procedure, method, or function. It's the same thing. Recursion is a procedure that calls or evokes itself. With each simple problem, it becomes simpler. So you're making it simpler and simpler, and we will see an example in the next one. So over here in the next slide, we see that here we have, we want to find factorial 5. So what is factorial 5? In this procedure called F, so we are calling this procedure F, and it takes, inside it takes an argument int num, and inside that, so you have the outside part, the int, and then inside you're comparing is the num equals to 1. We already said that our num was 5. So as long as it's not, we'll return 1, else we do what? We return num plus 1. And that is how you find F factorial. So let's step through this example. So here we see our F5. So what is F5? F5 in the next line is the same as 5 plus F4, and then plus 3, 4 all the way. We would write it in a straight line. Nick, do you mind writing it up there? What 5 factorial would break out into?
Okay. So yeah, so 5 plus f of 4.
Uh-huh.
Well, what is f of 4?
So what is f of 4? Is 4 f plus f of 3, and what is that? Is 3f of 2, and what is that? It's 2f of 1. And then you calculate that. So 2, that will be 2 plus 1. So 2f of 1 is 2 plus 1, which will give you a 3. And then you take that 3. So now what is 2 plus f of 2, which becomes a 3. So you get your 6. So now we know it will get a 4 plus a 6. And then so we are replacing the f of 4 now with the 6, and we get our 10. And so we'll have f of 5 is 5 plus 10, which gives us a 15. All right. So that is so f of 1 is our base case here, where you'd return 1. If when we reach f of 1, we have ended it, and then we go and then we end our finding of factorial. And if that was a little bit confusing, we're going to look at our next example that I hope will even make it a little bit clear. So here, our procedure is called factorial and int n. And here we are going to calculate 3. So we're going to start just simple with 3 so we can finish up quickly, but show you a different way of stepping through here. So int factorial n, if n is less than or equals to 1, is it? We know it's 3. Then we are going to return a 1. But since it's not, we go else. And this time we are going to take n. What our statement is n multiplied by factorial n minus 1, which is what? Is 3 times 3 minus 1, which is 2 over there. So then we go to the next one. This time our n factorial, what is it? Now this time we have our 2, and if the 2 is less than 1, what do? We would return a 1, but it's not. So this time, Nick, am I moving too fast for your pen?
No, you're good.
Okay, all right. So this time now, we are going to take our 2 times n minus 1, which is going to give us our 1. So we haven't reached our base case. So the next time we go in, this time we have n, is n less than or equals to 1? Yes. So we return our 1. So when we return our 1 using those arrows, so we are going to put our 1 into our n factorial here. So you see where we put our 1. So 2 times 1 is 2. So then we go up, and we are going to now put our 2 times 3, which gives us our final answer, which is 6. So 3 factorial is 6. Does that make it a little bit clearer? Anybody has a question? So that's
I do. I have a question. So at the beginning, it says if n is less than or equal to 1, return 1. So you got down to n equaling 1. So why didn't you return 1?
Yeah, you will return your 1, but that 1 makes you step back up. Nick, could you take that, please? Sorry.
Yeah. So you absolutely did, but remember, there are multiple nested layers of returns, right?
So you have to go back up?
To this recursive call,
Okay.
that is now a 1. But
Okay.
that's not our final answer because we're not back out to the largest doll yet, right? So that is a 1. But then that one said return n times 1. At that time, n had been 2. Now, n has changed throughout our times, but at that time, n had been 2. So it'll be 2 times we returned a 1 for this base case, 2 times 1 for the next level up. And that will now return 2 times 1, which is 2, to right here. We're still not out of the woods yet because we're still not at the original call, which was factorial of 3. So that is now a 2, and n was 3 right here. So this outer call is going to return 3 times that 2, or 6.
Okay.
Yeah.
So that's what this structure is showing, that for recursion, if you're going to trace it, and again, there are much more complicated examples of recursion than factorial, but the Praxis is probably going to keep it to a fairly simple recursion examples like this. But to trace it, you need to trace down every time there is a recursive call, every time you see that function name being called from inside the function, you need to trace it down to the next level, plug in the next number, which is n-1 in this case. And then once you start hit that base case, you need to, that's what these arrows are doing, is trace it back up to the original case.
Okay. Thank you.
All right, let's go to slide 9. So in this slide 9, I will just give you just a few minutes. Just look through and see if you can see what is happening here. And if you have a question, because the next one you're going to practice as a team. Look here and see if you have a question before we send you into the team. And I would caution you to always look at what else means, because even though this one has multiplication, what we're showing you, remember, it could be something else. It could be an addition. It could be division. It could be anything. It's not always a multiplication.
It could be like the Fibonacci numbers where there are
Yes.
2 recursive calls inside of one function.
Yeah, we don't want you to always think that it's the same like we gave you, because we gave you a couple of multiplication ones.
Is this one making sense? Let's see how we get the 120 here. We can step it through if we need to, but if we're all good, we can move on and do the breakout rooms for the next question.
I'm not good.
Okay.
I still am not seeing what's happening.
So,
Okay, wait,
yeah.
Nick, why don't we let them go into their breakout rooms when we come back, once they have class together, and then we can go through it, okay?
So we can
Is
go
that
to
okay?
number 9
Cool.
and 10, slides 9 and 10.
Yes,
Okay.
I'd like them to hear it from somebody else apart from us.
Yes, good.
Okay.
Okay.
All right. Let's go ahead and send you into your breakout rooms.
Would anybody like to sort of walk us through number 9? What did you think is the answer and why?
I think Rachel can walk us through.
Okay. So the way that I looked at number 9 was I looked for what are we going to, we want a situation where we're returning 5 times 6 times 7. And I looked at my answers to see that 5 times 6 times 7 is really an n-1 case. Every time I'm reducing by 1, if I'm starting with 7, and then I have a 6 and then a 5, I really only have 2 answers that have an n-1. So I can probably eliminate 50% of the question to begin with. And if I run through my case, if I start with a value of 7 to start with, and I go through the code, 7 is bigger than 5, so I'm moving into my else statement. 7 doesn't equal 5, so I'm moving into a missing statement. So let's try A, since I'm thinking it's probably A or D. So if I start with 7 for my n, I'd have 7 times the function of 6, because n-1 is 6. So now I need to just evaluate a function of 6. I'm going to put 6 back up in here. 6 is bigger than 5, so I skip my else, this return 0. So now I'm in the else statement. 6 doesn't equal 5, so go to my next else statement. So this would be, still looking at this, f of 6 would be 6 times the function of 5, and the function of 5 returns 5. So I'd have 7 times 6 times 5. That's how I look at it.
Excellent. And I was just writing, so I like how you narrowed it down right away. n-5, well, 7 minus 5 would be 2. So that's not helpful right there. Anything times f of n, you're not going down towards a base case at all. You're not getting simpler. It would keep calling f of 7 and call f of 7 again, and f of 7 again, and you would get caught in an infinite recursive loop. So that's no good. So I like how you eliminated it by looking for the f of n minus 1. And then how you did that 7 times f of 6 for the first one. And I just wrote a note that, well, if you were to plug in 7 for the last one for D, well, yes, it would be f of 6, but it would be adding instead of multiplying. And what would you be adding? It would be n minus 5. 7 minus 5 is 2. So that doesn't seem to match the problem description at all. So A is definitely the right answer. Yep. Okay, nice job. Yeah, and definitely anytime you can use those strategies to eliminate answers or sort of make the problem a little bit easier on yourself, then that is always a great idea. Okay.
All right, Nick, take it away on randomization.
Okay, so randomization, we don't have a whole lot to say about that. This is a little bit of a shorter topic compared to recursion and sorting and searching and algorithmic complexity. Those were the really heavy level topics for today. But we've just a few words to say about randomization. This is what Praxis ETS says, that you should be familiar with how randomization is used in computing. You should be able to identify how to use it appropriately in a variety of applications. You should know what the difference is between random numbers and pseudo-random numbers. Almost everything we use in computer science is pseudo-random, but there is a slight difference. You should be able to provide examples where it's useful and identify some applications like math libraries. Remember we talked about modularity last time in programming, how we can use libraries and APIs that might use a random number generation. So first of all, what is a random number? And relatedly, what is a pseudo-random number? A truly random number is a value generated through a random sampling technique from whatever set of permissible numbers. So you can think about rolling a die or rolling dice. That will, if it's a fair die, that will be a true random number between 1 and 6. Or flipping a coin. It's not like a weighted coin or a double-headed coin or something, that will give you a random heads or tails value, or equivalently like a random number between 0 and 1, right? You could think about heads as 0 and tails as 1. But true random numbers are difficult to obtain, especially in computer science, because they require some sort of physical process like that, or like some random decaying of atoms is a way you can get true random numbers. And also programs using them are hard to debug. If you're worried that you might make a mistake, well, it's often easier to use a pseudo-random number, as well as easier to find pseudo-random numbers in writing computer programs. So just about every computer program function that's called a random function, or random procedure, or random method of an API that you use is actually truly pseudo-random. So they're lying to you in the name there. But pseudo-random numbers are values generated that the properties are approximating the properties of a random number, in that like every number is equally likely after a certain point, and that there's whatever normal distribution of all possibilities and stuff like that. But not normal. What was the word I was looking for? Normal is like a bell curve. Sorry. But it is not truly random because it is determined by some initial value, which is called the seed. And so if I were to run this program on my computer with the same seed, and Deborah were to run the same program on her computer with the same seed, we would actually get identical answers. So I could predict what is the so-called random number that she generates from this random call. However, there are ways to randomize the seed to make it much closer to true random numbers. And that can be by moving mouse movements around your screen, or by random key typing, or even eye tracking software that tracks your eyes. So my eyes will look in slightly different places than Deborah's eyes will look. And so we'll both start with different seeds and have much closer to a true properties of a random number, but it's actually pseudo-random. So most programming languages do provide a random number generator, a function call, or a method call in whatever API that programming language uses. So for example, in Java, There's the math library, which has an API of predefined processes that are commonly used. And the math library includes things like the constant for pi or the sign function, but also includes a pseudo-random, although they just use the word random number generator. Again, the difference is that random is truly unpredictable and uses some sort of physical means, like atmospheric noise or actually rolling a die. Pseudo-random uses mathematical algorithms completely generated on the computer. So let's look at a quick application. So and we're going to talk a lot more next week when we get into data, simulation, and modeling about some applications. But just a quick view of the application. Randomization can often be something like generating a random permutation of some sequence, like shuffling cards, selecting a random sample of a population using statistical sampling. And so we have one example here where maybe you're asked to calculate the probability that 3 specific swimmers, let's say the numbers 2, 3, and 8 right there, those swimmers, are going to be the medal winners to get the gold medal, the silver, and the bronze. And the way you would do that in terms of calculating the probability would be, well, there are 8 possible ways to award, this is permutations, the gold medal, 7 to award the silver, 6 to award the bronze. So 8 times 7 times 6 is 336. There are 8 factorial, or 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or 40,320 different ways that the swimmers could place based on their times total. So the probability would be the first number divided by the second number, 336 divided by 40,320. That would be the probability that those particular swimmers are the medal winners. And again, what does that have to do with randomization? Well, I could calculate that probability for something maybe as simple as this, but often in real life, there are more variables and we might want to do a randomized simulation. So we could write a computer program that would randomly or pseudo-randomly generate that swimmer number 4 came in first place and swimmer number 8 came in second place and swimmer number 7 came in third place, right? And randomly generate a permutation of a particular run of this swim race. And it could actually run that simulation thousands of times and then calculate an approximate probability of how many times our actual swimmers that we care about won the race that would approximate this true probability. Okay, so Deborah, you came up with that example. Is that a good summary of it?
Good job. You did a good job. Fantastic. Thank you.
So today we're going to cover digitalization, data encoding and file compression, data encryption and decryption, and computational tools for working with data. And we have here from Praxis exactly what you're supposed to be familiar with in those 4 topics that we're going to talk about today. But rather than read that to you, we'll just show that to you, and then we'll dive into the topics.
All right. So digitalization. We have a funny little data. Next slide. I think you will find that mine is bigger. So how do you know which data is bigger and all that? You will have to, once you digitalize it, then maybe you can compute it. But really, by just looking, you can't tell, yeah? You can't tell. But when you talk about data, you're talking about massive data. So let's go to slide 6, Nick. So data digitalization is the process of converting traditional data types, such as handwritten, printing, sounds, images, to standardized digital data that a computer can recognize. And normally, digital data includes text, video, audio, images, anything else, you know, even those funny characters on your stuff, each that can be used on computers, and it's formatted in such a way that computer can read it in zeros and ones, as we know. This is achieved by putting the data into bits, which in result is representation of an object, an image, sound, document, or any analog signal. So digitalization is of crucial importance to data processing. So for you to be able to process the data, all this data you're collecting, what people are doing on Twitter, people are doing on the web, people are doing with Internet of Things, and then process the storage and transmission, because it allows information of all kinds in many formats to be transmitted with the same efficiency and also intermingled. Though analog data is typically more stable, so it's usually more stable, digital data can be more easily shared and accessed, and also in theory can be more propagated indefinitely without generation of loss, provided it is mitigated to new stable format as needed. This is why it is a favored way of preserving information for many organizations around the world. So now you find most people digitize it, and this is what they're doing. They say to digitize the key, but which one is it? So it's the process of converting traditional data into bits, and people are still having a lot of difficulties doing that because we are producing a lot of thousands and thousands and thousands of terabytes every single day. So go to the next slide, Nick. So a binary digit is called a bit, and it's 8 bits, which makes a byte, and bytes are the standard by which data storage and data transfer are measured. And we later on we'll talk about measuring and all that. Examples would include 5 megabytes for a digital image, 2 terabytes of storage on a laptop hard disk drive. Some smaller sample text files might be 1 kilobyte. So if all data is stored as primary number, computer scientists must know how to do some arithmetic with binary values. We will do some of those next week, how to compute data and all that. So go to the next one. So computers store data in a file in digital form using zeros and ones, as we talked about. And a text file is made up of individual characters, which are stored in the computer in binary form. So even characters, not only the numbers, get converted into zeros and ones. The size of a file matters. That is text, graphic, audio, video, graphic compression. And ETS exam, practice exam does require you to know a little bit of that information. So we will talk about that next week. The file space, or maybe Nico might cover a little bit, I'm not sure. The file takes space on the hard drive, and it takes time when you email it and view it or upload or download it from our website. Many people nowadays use faster transfer, but some people still use modem dial-on connection. Yes, it does still happen. And email suppliers may detach big attachments, and the space on your website page may be limited by your server. So all this information has something to do with data, and you should know why, maybe why information does not transmit as it should. So the next part, Nick is going to talk to you about how data is compressed and then how it's able to be transmitted. So Nick, take it away.
Yep. So as Deborah said, next week we'll dive into a little bit of calculations with kilobytes and megabytes and gigabytes, but at its basic level, as she just said, data to be digitalized needs to be encoded into zeros and ones. And sometimes we might want to save space on our hard drive by compressing. So our encoding could be a compression algorithm or not, right? So let's look at data encoding. And by the way, this information here, this picture comes from Khan Academy, and we're going to give you some references to some sections of Khan Academy that have really good information about data encoding and these topics we're talking about today. But what is data encoding? It's representing data as bits so that it can be stored on a computer. And the encoding algorithms are usually they're usually public, right? That they're usually something that's very clear to people so that everybody can encode their data in the same way, and they can also translate backwards and look at those bits and decode it back to the original symbols or whatever it is. So here's a very simple encoding. Again, this comes from Khan Academy, where 0, 1 represents this peace symbol, 1, 0 represents the heart symbol, heart emoji, and 1, 1 represents the smiley face. So can you just take a minute, think about this to yourself, that if we write a file called message.hpe for heart peace emoji, I guess, I don't know, with this data, if you look at those bits right there, what is the message actually saying in human readable emojis? Of course, you need to know where to start. So we'll start with these are all groupings of 2. So we'll start with the 0, 1, right, which is the peace sign. And then there's another 0, 1, another peace sign. So peace, peace. 1, 1 is the smiley face. Another 1, 1 is the smiley face. 1, 0 heart. 1, 0 heart. So yes, Michelle, that's right. And so did you, Paula, in the chat. Good job. Okay, now obviously that's sort of a very simple example. Most likely you wouldn't be storing emojis with so few bits because there are a lot more emojis beyond those 3 that we would need to deal with. So you need to think about in data encoding, how do you encode numbers? Well, that could be pretty simple. Just if a number, if it's an integer, right? Just convert it to binary, right? Like we did way back when on 3 weeks ago, I'm confused by this point, all the Saturdays blend together, but we did binary, right? Conversion from decimal. So if you have a decimal number you want to store, you could just convert it to binary. But what about text? And as Deborah said, you need to encode every character as some sequence of bits. Well, there are schemes for that. There's like, for example, the ASCII scheme. You're not expected to know ASCII for this test, but it is a very common one where the letter capital A would be encoded as the binary number for 65. And of course, a lowercase a is different from a capital A. And the exclamation mark, you need to get every single thing you can type on a keyboard, not just the letters, but all the digits and all the symbols as well. And so ASCII is one scheme for encoding text, but there are others, right? There's Unicode, right? Is another one. Encoding, what about encoding formatted text? So like in Microsoft Word or in PowerPoint, we can make that text bold or italicized. How do I encode bold with italicized? So how do I encode images? Images are encoded 1 pixel at a time. Every pixel, every little tiny square of that image has to be encoded, often by its red, green, and blue lightness values, brightness values in each of those channels, red, green, and blue. And then all the pixels get put together into an image. What about encoding sound? Well, sound, you need to think about volume of the sound, pitch of the sound, timbre of the sound. Musicians know a lot more about sound than I do, so I'm going to stop right there and not talk more about sound. What about videos? Videos are images and sound put together over time. And yes, you're often going to use vectors or multidimensional arrays or matrices to encode several of these things, yes. So, so there's a lot to talk about encoding. I do encourage you to check out the Khan Academy examples that are linked down here, and we'll also link to them from the last slide about recommended homework. But just when we're talking about encoding, we do need to think about file compression at the same time, because data encoding schemes the simplest encoding would take up lots of space generally, right? Especially when you're getting into audio and video and things like that, or even images. So if I encode and the size of cameras nowadays, like a 12 megapixel camera that I have on my phone, is going to take up a lot of space. So they have algorithms like a JPEG algorithm that you're probably familiar with, at least as a file extension for images, that actually compress the data in those images. So rather than that simplest encoding we were just talking about, it will take up less file size, less space on your computer's hard drive. And when you talk about compression, there are 2 types of compression. There's lossless compression and lossy compression. Lossless will reduce the size of files without losing any information, which is sort of amazing to think about. How can you make the size smaller without losing the information? And there are some really ingenious ways to do that, to think about, well, if all of the pixels on this part of the picture are all red, I don't really need to encode the red, green, and blue values for all of them. I can sort of just encode their positions and one red, green, blue value for that particular shade of red. So there are lossless compression algorithms that do reduce the size of files, but do not lose any information. that you can actually be completely faithful to the original and reconstruct the original from that lossless compression algorithm. But lossy compression algorithms are also very common that do reduce the size of the file, and they do discard some information. It's not perfectly a perfect fidelity, but it discards in some sense the least important information. So you can still do a pretty good job of recovering the picture or the song. And that in some ways sort of connects back to what we were talking earlier about heuristics, right? As long as it does a pretty good job, you still can see the image. Maybe you can't even tell the difference with your naked eye. You would need a computer to actually see the differences between these. And I put a couple examples here. I'm not going to read these out to you, but some common algorithms like for images, these two are lossy, but here are some algorithms for images that are lossless. And similarly for sound and other examples here. And with that, let's talk about data encryption.
All right, so let's go ahead and talk about data encryption and decryption. We'll look at some information that you're required to know. Encryption is the process of translating plain text into something that appears to be random and meaningless, like ciphertext, but decryption, or I mean ciphertext, but decryption is the process of converting the ciphertext back to plain text. A symmetric key is used during both the encryption and decryption. So encryption is the process of converting normal data into unreadable, whereas the decryption is a method of converting the unreadable code into something its original form. So decryption is done by the person who is sending the data to the destination, but decryption is done by the person who is receiving the data. So they'll open it, they'll have a key, they'll open it, they can read it. And the reason this is done, we all know, is for security. When you're transferring information through the web, you want to decrypt it so that people are not able to read it. So encryption, again, here, it's a little bit of repetition, but as you can see, here is a network. You see the sender is sending plain text, which then gets encrypted, and then the person who's on the other side will take that that information and will decrypt it back to plain text, and now it will be received. So that is the process, and that is to the level that you're supposed to be understanding this information. There is much more that you can do with algorithm and all that to change this, and no, you're not going into that deep length. You're just going into this stage. And the next one, the next slide over here, we'll look at the another difference between data encryption and data encoding. Nick talked to you quite a bit about data encoding, but let's look at here. When you have encryption, is the process of changing it from the original message to look like random meaningless sequence of bits. So for secrecy, well, data encoding is going to be the process of representing that original data into bits through a known or orderly process. So there's a process that they go through so that they're able to read it on the other side. And encryption uses a secret key, so only the recipient, or both the sender and recipient, can successfully read the plain text message, but others are left in the dark. So then when you encode data encoding scheme, keys are usually public, though they may be a company trade secret. So anyone can map forward and backward from the original data to the bits representation of that data. So symmetric versus asymmetric encryption, while in data you have the lossy and lossless encoding. So please review those again and understand them, because this is a level that you're supposed to understand about data encryption and data encoding. And now we will go to tools, and Nick will take you through the tools that we use for data analysis.
Okay, so this part right here is going to be what Praxis, what ETS expects you to know. about using computational tools, including spreadsheets, to analyze data. And why do you use them? To discover, explain, visualize patterns, connections, and trends. So there is a really good, again, this is linked right here. It's also linked from our Khan Academy resource that has some really good information about some of these spreadsheet tools if you're less familiar with them. But it does include a little bit of databases and SQL tools, SQL tools, and that part is beyond the scope of the Praxis. So if you use that resource, just a warning that it will be good information to know. I enjoyed learning about SQL, but it's not needed for the Praxis exam. So let's dive into these three things. We've got a couple slides here more about data tools. So you should be able to describe different spreadsheet operations, like using formulas in a spreadsheet, like a formula to find the average, or the formula to add up all the numbers in a column. You should understand about sorting in a spreadsheet. Sorting data will rearrange the rows or the columns depending on which way you sort it. For example, you might want to put all the names in alphabetical order, or maybe you want to sort the data by amount from smallest to largest, right? Filtering in spreadsheets is a little bit similar, but instead of putting them in order, it just shows some rows or columns that meet your filter criteria and hides others so that you can look at only certain data that meets your needs. Now there's a pivot table that I've only seen pivot tables be used. I've never made one myself, but it's sort of a combination of multiple ones of these things that it summarizes and views large amounts of data in an easy to read format. It creates a new view just by focusing on certain rows or certain columns or certain aspects of your data. Do you have anything to add, Deborah, about pivot tables?
No, not really, because they don't need to know much beyond what you have just explained. So they are fun to use. They can make you cry sometimes, but you don't need to know that.
If you cry, wow, okay.
Yeah.
Okay, so those are some common tools within the spreadsheet, sort of changing those numbers around or dealing with those. One thing to think about when you're using data tools in spreadsheets or otherwise is that the data often needs to be cleaned or filtered or sorted to be usable and to eliminate errors, right? So possibly removing, you could sort all the numbers in order from largest to smallest and then look at what are the biggest ones or what are the smallest ones. Maybe those are outliers that might distort the statistical analysis. Maybe they are not true data. Maybe this sensor was just left on for 48 hours when it should have only been on for 10 minutes and therefore recorded such a bigger number than all the other sensors that were operating correctly. So I use those to help you remove outliers or help you remove errors that can help you apply a better statistical analysis. And the errors can occur from sensors like that, or even just data entry typos when we're typing them in the spreadsheet. And so being able to look for those and apply filters and sorting mechanisms can help you do those things. Finally, on data tools are charts and graphs, which are produced after you sort and filter and remove errors and things like that, used to visualize or display data. And that is, again, we're not diving deeply into how to create a pie chart right now, but you should be aware of visualizing data and making things easier to digest and understand. So Heather just typed a great example in the chat of using pivot tables. Sum of time spent over the course of a week and produce a table for every team, for each student athlete and study hall. Cool. So with that, we're gonna do some sample questions. And I thought we would just do these sort of all together right now, if that's okay, Deborah, instead of breakout rooms.
Yes, it's fine. That would be good.
So why don't we look at number 18, take a minute to digest it. Okay, I'm seeing a lot of C's, a lot of lossless, okay, and that is the correct answer. You can read more about Huffman encoding if you're interested on the Khan Academy, but again, you don't need to know all the details of how it works. All you need to answer this question is described to you in the question here. And by the way, both of these come from that ETS resource, so this is the sort of level you're expected to read this question and analyze it and understand these terms, but you don't necessarily need to know what Huffman coding is for the Praxis exam. So yes, it is lossless. Anybody want to speak out loud and say why, how you know that from the question?
Is that because you are collecting the same amount of data and information, you're just identifying each bit of information in a more efficient way?
Okay.
And the more that it shows up, the more data it's going to take to store those values. So you want a smaller chunk of data.
Yeah, yeah. So it's definitely more efficient. That is a lossless compression algorithm. It is compression because you get that efficiency. If you think about like letters of the alphabet, that's not exactly how it works. It's more about the binary numbers. But like letters of the alphabet, E occurs the most. So if we just assign a single bit encoding to E, and then we can assign a double bit encoding to the next more frequent ones, and then a triple bit encoding to the less frequent ones like Z and stuff like that, or a quadruple bit, then we're definitely getting efficiency, but it's still lossless because you can still reconstruct the original exactly without losing any information. And there's nothing in here about why you would lose any information. Because the frequently occurring values just get fewer bits. But everything has a one-to-one correspondence between the encoding and the value that was encoded. Anybody want to explain their answer?
I can explain it, Nick.
Okay.
So when you're looking for outliers, you don't want to use a number that a function that averages things because it would account for those outliers. It would make the average incorrect, actually. And then it's not B because it's just counting the values. So it's not looking at whether or not they're small, high, incorrect, correct. A function that rounds the numerals doesn't really matter because it doesn't really say what kind of numbers we're using anyway. So a function that sorts the values would definitely show whether there are some values that are not similar to others. That's my thinking.
Good explanation. And that's to the level that you're supposed to understand these questions. So no pivoting and all that. So you do need, if most of you just teach computer science, engineering and other things and don't do the business part of it, just know you need to understand a little bit of this, you know, understand a little bit of the spreadsheet, the Excel and how it works.
Yeah, and just to echo what you were saying on the averages piece, the example, like I remember hearing somebody say this once. So, right, if Bill Gates walks into this room of 10 people, the average salary or the average income, right, just jumped up to several $1 million. It doesn't mean any of us make $1 million. It just means the average or the mean would be so much bigger. And that's because of that outlier. So if we want to detect that outlier, detect the improbably high or low values, then an average is not going to do it for us. But sorting them and then looking at the top of the sort list, the beginning of the sort list, and the end of the sort list, and just considering those values individually would do it, yes.
That's a fantastic example, Nick. I like it.
So with that, we are at the end of our time for today. We just have a couple of closing slides to remind you of all of these study resources. This is the same we provided you before, but on the next slide, here are some recommended ones for specifically tying to what we did this week. So obviously, we know a lot of you are so busy with virtual schooling that you might not have a lot of free time, but if you have some time, please check out the Advanced Praxis Programming Google Classroom. That not only includes programming and pseudocode, but also includes advanced algorithms like sorting and searching, and I think even a little bit of the complexity that we talked about today, but definitely recursion as well, yeah. So check out that Advanced Praxis Google Classroom that MCCE has created for you. Under Khan Academy, again, this document is just a study guide. The outline was provided by me, but all of the resources come from Khan Academy. but it just links you through each of the topics, like impacts of computing we're going to get to next week, and which con lessons are relevant to those praxis topics. So for this week, we're recommending you look at algorithms part B to reinforce what we did with these advanced algorithms here, and also data part A. That's what we just covered. We'll cover data part B next week. And in the UT Austin course, if you're using that as a resource, module 2, algorithms part B, and module 4, data part A. I mean, same thing as 2B and 4A here. They're both aligned with that praxis outline as what is relevant to you. So Deborah, go ahead. Any closing?
All right. And as usual, remember, please remember you're not alone. If you're doing something and you get stuck, we are just an email away. You know, we can always help you. That's why we are here. We really do like to participate. Put your question any time of the week, not only on Saturday, in the parking lot. Nick and I do look at them, and we will get back with you. We can arrange to have a call with you. We can arrange whichever means that will be able to help you. So please don't hesitate. The parking lot, our emails, sharing with other people, and also there's these are our emails, and they're in the emails you get from Nick all the time. Nick is so good at sending us email, even though we have the information already, but we appreciate that because